I'm going to introduce our next speaker, Hussein Osman, who leads the sensAI solution development for Lattice Semiconductor. He has over 20 years of experience bringing technologies to market with a personal focus on medical applications. Hussein is going to share with us how Lattice FPGAs can help you stay apace with rapidly advancing deep neural network models, while also remaining in an ultra-low power envelope, as well as how Lattice's toolset can help you with what can be complicated processor design and also with model optimization. Please give a warm welcome for Hussein Osman.
Thank you, Eric. Thank you for taking time to come to this session. I know it's late in the day. And thank you to the Alliance for allowing me to have this discussion with you. As a society, over the last couple of years, we've faced some significant challenges. And we had to be flexible and agile in overcoming these challenges. As engineers, we also faced some challenges. And we had to come up with flexible ways to design systems in the face of fast innovation cycles. In my talk today, I talk to you about Lattice's FPGAs and tools and how they enable acceleration of future models with existing silicon, flexible FPGAs that are programmable. So we've seen a fast innovation in a cycle of moving models from the cloud to the edge. In addition to the drivers that I think most of us agree to, latency, security, bandwidth limitation, privacy, we also see lots of options that are available for system designers to accomplish the goals of the system at the edge that they used to do on the cloud. This conference shows you the wide variety of available different silicons that can accomplish these capability. Why FPGA for the edge? So first of all, in terms of power consumption, an FPGA is a parallel compute engine that's able to run at lower clock frequency, translating directly to lower power. FPGAs have flexible resources that are spread throughout a fabric. They include DSPs, they include memories, they include programmable logic devices that are spread out and interconnected, resembling in a lot of ways some of the new ASIC that are built for AI purposes. Those resources allow us to create different accelerators that run within the silicon. You can run pre-processing blocks, take a signal in, clean it up, then run it into an engine, post-process it, and then react to the environment based on the output of the network. We at Lattice created multiple scalable use cases running in parallel within these FPGAs. Security is an important topic for us, and we build security blocks within our engines, within our FPGAs that allows authentication of a bit stream as the device boots up. And it also monitors the bit stream that's sitting on a flash or the ML firmware that's sitting on a flash continuously to understand if there is an attack that happened to that and reacts based on that, goes and finds a secure copy of the boot code and boots from it. Very importantly in the topic of my discussion is hardware programmability. For us, changing the AI accelerator is days of work, modifying an RTL, changing a tool, and all of a sudden, we're supporting a new model, a new layer that was not supported previously. So this is how we keep up with the innovation that's happening in the world out there and accelerating innovation. To think about this, think about our engine as the knob on the left-hand side. This engine is modified in RTL. It's a hardware descriptive language. You go write code, and you compile this code for our devices, and now you have an engine that does different function that previously was not able to do. Combine that with the evolving models that are happening, all of a sudden you have a new layer or transformers show up that previously were not there. That is a change that we can accommodate with the change to the silicon. And in terms of the entire system solution, that means improvement in use cases, and it also means introduction of new cases into the system. when we compare FPGA design cycles to ASIC design cycles, given that these FPGAs are programmable in the field and you can continuously update the design over time, versus a fixed silicon that it is what it is, that's what you get. A system designer can iterate multiple times, introduce new cases, and get to market leadership in the same time frame when a system designer using an ASIC would have to wait for iterations of those ASIC in order to get to the same performance capability. Looking at computer vision specifically, and I looked at some of the systems that are running here and some of the demos that are running here today, based on the data for a similar silicon to the devices that we have a family called Nexus devices. The processing capability of a computer vision system, which includes a pre-processing block, a AI engine block, and a post-processing block, running on a pure CPU of the same class, you get about 10 to 15 frames per second average for the same network and the same resolution. If you look also at CPUs that have some acceleration blocks that are built into them for the AI engine, you'll find that a lot of the pre-processing still runs in software, and a lot of the post-processing still runs in software. Even with a large AI engine, it's not utilized most of the time, and so the overall system performance for a similar network and a similar device is about 20 to 30 frames per second. We have demos here, and we're showing our capability that we can run multiple AI engines in parallel. We can run concurrent threads that reduce the overall latency of the system and produce faster frame per second in the full system implementation. So it is important to us not to just provide a silicon and let designers go figure it out. We've been, since 2018, producing the sensAI stack, and it's a collection of tools, hardware, acceleration IPs, software tools, example reference designs and demos, and custom design services, and end-to-end solution that we built to enable specific end markets. All of those are available for a number of our products that are listed in the bottom. Those products produce a range of experiences and power consumption that is related to those devices. I'll go a little bit deeper into a few of these items over the next few slides. One of the silicons we introduced recently last year is Certus Pro NX. It's a class-leading silicon FPGA in terms of power consumption. It provides 2x the performance at half the power consumption over our previous generation devices. It provides system bandwidth that is class-leading in terms of input from image sensors or other sensors, inputs and outputs to memory, and then system interfaces, and I'll give you an example of that. Overall, when we built this device, we were thinking about edge compute when we optimized this device for edge compute. One example application we find this device used in is smart cameras. In this application, we interface to an image sensor. We can interface to a MIPI CSI image sensor over multiple lane at 1.5 gigabit per second each lane. And we bring those data into an ISP, and we can also instantiate an AI engine. And we can take that metadata and interface to the rest of the system, having the compute run privately and securely on an edge device versus sending all the data to the cloud or the rest of the system. We also have LPDDR4 for the type of FPGAs and class of FPGAs I'm talking about. This is first in class to provide such capability. And so we allow for ability to run larger models within our device. In order to design a system with our FPGA, an acceleration system, an AI system, we interface to regular training frameworks, Keras, TensorFlow, Caffe. A system designer can take their trained model, bring it into a compiler tool that we provided as part of our stack. The compiler tool will help with quantization and finding the right device to accomplish the goals of the application that the designer is working on. The bottom side of the slide is our FPGA tool cycle. FPGA is pure blank device, and you can create pull IPs from our library, put them together, connect them together, and instantiate basically design into an FPGA, and now you have a new chip that does different function. This is a very hardware-centric, and it requires somebody to understand FPGAs and understand RTL in order to build this. We know a lot of the system designers are actually software designers, not FPGA experts. So what we provide is a tool called Propel. It's a pick and drop, connect circuits together. It's a FPGA SoC builder with the ability to instantiate something like a RISC-V processor, an ML accelerator, a vision accelerator, interconnect them together, and create a system, bring in data, and process that data and take the result out of the system to the rest of the components in the system. This kind of implementation allows a system designer who is a software engineer to bring a TF-Lite model that's a C, C++, Python type of model into our flow and integrate that into the FPGA. This is, while it's less optimized in terms of capability versus the hardware, it definitely provides some good ability to ease of use overall. We also put together a tool called sensAI Studio. sensAI Studio is our tool to bring in either one of our models that exist in our model zoo, or a customer can bring their own model, go through transfer learning, evaluate how well the model is trained. There is a data capture and labeling tool that's available as well. Then the user can go through, configure, test, evaluate how well the model was trained, and then compile for a specific device and put it onto a board, and within hours are able to go verify their use case. So we wanted to make this as easy as possible and provide tools designers can use to go through the entire workflow. One example that we're running on our booth today is the Certus Pro NX device that I talked to you about previously. It's running 33 frames per second, 224 by 224 RGB, and it's optimized and targeted toward industrial and robotic markets. And so you can easily see this device running object tracking and object classification real time at 33 frames per second. So we picked an end market that we felt our power and performance envelope is perfect for, and we've been focused on this market. And so we worked with our partners to enable smart next generation PCs. Part of the reason why we pick PCs is we understand the importance of PCs, especially now post-COVID. We spend more time in front of our PCs over we spend in front of our notebooks or our tablets and our phones. So PCs have become really, really important piece of our daily life. The trends in the PC, what users are looking for, they're looking for smart and aware devices. Devices, when you show up to them, they're ready to use. Devices that understand you left and you're not looking to use them anymore, and they guard your privacy and your security. They're also looking for great collaboration in terms of good quality audio and video while you're in conference calls. System designers for notebooks are challenged by all the new form factors they want to introduce into the market, and that brings in system challenges. How do you move all this data through from the camera to the rest of the system? So we've introduced solutions in this area to try to solve all these problems. And some of the AI-based solutions that we put out there, and this was introduced at CES earlier this year, we have a solution that does presence detection. So when the user shows up to the PC is ready to use and woken up, and you can log them in using Windows Hello. And once they're in front of the PC, it tracks their attention. When they're not paying attention to the machine, they turn their head to the side, it dims unused resources like the screen. It throttles back the resources that is not needed until the user is back engaged and ready to use the machine. And this saves significant power and battery life. It turned out about 28% battery life improvement based on a 45% of time distraction while using. We also created a use case around onlooker detection, where when a second user shows up behind the main user, the main user gets a notification telling them that there's somebody behind them, and they can choose to dim the screen, or the solution would dim the screen for them automatically. Also around conference calls, a lot of times you sit in conference calls and you see users who are sitting very far away and in the field of view, they're not taking a big part of field of view. We have the auto framing solution that finds where the user is using AI, and then it frames the video feed for where they're at exactly. So some of these applications show where our capability in terms of performance and power does have a really good fit in battery constrained solutions and system solutions. So you can see a lot of these demos in the booth today. And for more information, more details, you can go to our website, latticesemi.com/sensAI is where this solution and information about this use cases can be found. Thank you.
Thank you very much, Hussein. If you have any questions, please come right up here to the microphone. We have plenty of time for questions this afternoon. I'll start off with one. Looking just at the very end here, we talked about the smart PC use case. That's a fairly straightforward use case. It's something that we see thinking about just all sorts of devices that wake up. Let's talk about more exotic use cases. Some of the earlier slides are talking about more high-end things. What are some of the more exotic use cases that you're looking towards today that are in the marketplace that Lattice is good for?
So other areas that we find ourselves to be a good fit for is a lot of things that are vision-related: cameras, smart doorbells, robotics, things where we can solve multiple system issues. We can do some motor control. We can look out for objects that the owner of a robot or a person that the robot needs to interact with. So very similar use cases in adjacent areas that make sense for us to take our current solution and kind of move them over. And it also requires, in some cases, to increase our performance or implement larger networks and change the way we interface to the rest of the system. So these are the smaller increments that we're making initially here, and we will continue to just improve in terms of our FPGAs and capability of our tools and add additional devices that provide even higher performance.
Great. Let's see. How about this? What's a great example, for the tool set, what's an example of a tool set being applied to, say, by a developer that you've got, being applied to one of these relatively straightforward examples, or even a more exotic one where they got a big win because, say, they didn't have a big team or they didn't have the right staff?
Yeah, I think sensAI Studio is a really great tool. When you're here at this conference, everybody knows AI and everybody knows so much about AI, but in reality, a lot of system designers don't have as much information or knowledge to build AI systems. So I work with one company that wanted to detect berries in the field, and what we guided them to do was go to sensAI Studio, pick a model, bring a data set of the type of berries that they want to detect, go through the training steps, verify that the model works the way it should work, and then find which device is actually best for them and introduce that model to the device. We had a board that has a camera on it, and they were able to download the model. And within few days, they had the model connected to one of their vehicle and out in the field and doing testing to collect data and see how well this model worked. So tools like these are really important for your everyday system designers that are looking to build something for agricultural reasons or industrial reasons that don't have as much depth of knowledge when it comes to AI,
Sure.
The applications.
Yeah, certainly in an industrial space, people are very focused on the use case. They don't have the hardware expertise, perhaps. Okay. I want to go back to the question that the slide that you had about your competition. I know that Hussein had to submit these slides before he could walk around the floor here. Mm-hmm. What did you find when you were here? We have 82 folks out here. Not all of them are your competitors, but do you feel like you were validated? Or are you seeing new things you weren't expecting to see?
No, in a lot of ways, I was really validated. I do see many CPUs, pure CPU demos that are running, they're doing 10, 15 frames per second, and that's what I had in my slide. And I've seen CPU plus GPU, or CPU that's accelerated with a small NPU next to it, and 20, 30 frames per second was an average of what I saw out there. And I definitely know our demos are able to do a VGA at 60 frames per second using internal memory only, no external devices, at a few hundred milliwatts, so 400 milliwatts, and most of these devices were getting close to the 800 watt type of power consumption.
Question? Yeah, please.
Yeah, if I go for custom accelerator, custom design, do you support only RTL development or also high-level synthesis? Okay, this is the first question. And the second, are there system on chips with your FPGAs and hard cores, like Zinc, kind of?
Yeah, good questions. So in terms of HLS, for the size of FPGAs that Lattice has produced, they're constrained in terms of resources. Having an HLS on top of it is a waste of these resources. You would rather have something designed that's optimized for the hardware. Of course, we have the bigger devices, but that increases power and so on. So for the most optimized solution, you would want to implement things in hardware, and we do provide internal design services and partner-driven design services to get you there. For AI specifically, we provide this flow that's software focused. So you can build an SoC, you can take a RISC-V processor, instantiate it in our FPGA fabric, and use it along with accelerator to accelerate the use case. Does that answer your question?
No, but if I don't want to use your accelerator, I want to go for my custom AI accelerator.
Okay.
So you say no high-level synthesis, right?
No high-level synthesis.
Okay. Yeah.
We can talk about how to bring your accelerator into our tool chain, but the way it's set up right now, it's definitely taking our accelerator and bringing your model to use and take advantage of our accelerator.
Hi, so I guess I have a follow-up to the moderator's question about the competition. So if I understand correctly, your chips are strictly FPGA fabric. There's no CPU. So, obviously the elephant in the room is Xilinx, now AMD, where you're going to have some ARM A53 or A77 cores along with some amount of FPGA fabric. So, what are the and clearly there are some cases that actually need to use the CPU also, because FPGAs aren't great at everything. They're really good at certain things. So where do you see your place? When is it better to go with a pure FPGA, versus some of the alternatives?
Yeah, I think what the competition is doing with including an ARM processor there, it's not for acceleration of AI purposes. It's for the last point. It's the post-processing. It's taking action after something happened, and for ease of use, mainly for how to use the fabric for acceleration, for HLS purposes. A lot of our competition are not focused on the markets we're focused on. We're focused on the low power. I'm talking, a few hundred milliwatts and below. And in that range, our devices are very well designed in terms of processes we use. We use 28 FD-SOI process, which is a low power process. And the mix of resources we have, DSPs, the memory that we have to accomplish the goals of something like a PC or a robot or a camera needs to accomplish on device. So a little bit different approach between what the competition is doing and what we're doing. But yeah, for those power performance envelope that I'm mentioned, it really makes sense to use our type of FPGAs and pure FPGAs. So you can keep with the innovation and you can change things as fast as possible.
We certainly have time for one or two more questions if anybody has a burning one. I'll ask one about the toolkit. I've moderated now 13 talks in the last 2 days. A number of them have been about toolkits from processor companies. A lot of them are aimed at small developers. This seems to be something that maybe you have learned from your market research, but also your competition has learned. Small developers are struggling to use the tools to the best of their ability, or, hey, I bought your chip, I'm not getting what you told me I would get out of it. So my question is, we have a range of people here. Certainly many of the attendees here at the summit are actually from pretty big companies. Are these tools also really useful for big companies, or is it just for those teams that are just too small to do this work on their own?
No, certainly the system designers that I've been engaged with over the last few years are from very big companies, and their exposure to AI and the capabilities that can be, or the use cases that can be done, was limited at the point we started engaging with them, and initially it took us building an entire solution for them to kind of convince these companies that AI is real and edge compute is real and you can do a lot of things using this. But once they get over that, they start looking for, hey, what other tools do you have? What can I do? How can I go modify and change things? And that's when these tools come in very handy. So us building those tools up front and then building a solution, it made it really easy to go back and say, oh, by the way, if you want to add anything else, here are the tools. We've been working all along on those and improving them and adding more features to them.
Yeah, once the engineers the wheels start turning and they feel unlocked, then they can see that they can do more.
Yes.
We've got time for maybe one more question. Anybody? All right, well, let's say thank you so much to Hussein Osman from Lattice Semiconductor.
Thank you.